Okay, so I guess here's that diagram I was talking about. So the last couple of weeks, we've been talking about just the hydrocarbons. So hopefully you feel fairly confident in your ability to name aliphatics and aromatics, and hopefully you know this terminology, by the way. So aliphatic means no benzene ring. Aromatic means yes to a benzene ring. And hopefully you're fairly comfortable with the alkanes, enes, and ines. I should really also update this diagram, I think, because there's one more thing we could throw on here. You could also talk about anything that's a cyclo. Anything that goes in a circle. You should know how to name that as well, right? Which ones are saturated? Which ones are unsaturated? Well, the alkanes and the aromatics, those are saturated. We consider those to be full. And if it has double bonds and triple bonds, it's unsaturated. I don't know that I could actually blanket say whether or not the cyclos are one or the other, because it depends on whether you throw a double bond into a cyclo. But, how'd that test go on Thursday? If it didn't go well, we definitely need to sit down and chat, by the way. So if I have time today, we should go over anything you didn't get. Because I would say this section here is kind of like math in a way, where if you don't understand how to do the previous kind of topic, going on to the next one doesn't all of a sudden make it better, because all we do every day is just add one new thing. Right? So today we're going to talk about how to do the organic halides, which are now the derivatives. We're going to add things like oxygen, nitrogen, chlorine, bromine. And I mean, we only talk about a few of these things. Organic chemistry, I mean, it keeps going for forever, right? I remember when I was in university, I learned about how to add magnesium to something. And I remember at the time I was confused, because previously it was always nonmetals. Like all of these things right here are all your nonmetals. And all of a sudden my professor's like, and now we're going to add a magnesium. And I'm like, how's that possible? That's a metal. You know? But I mean, if you can dream it. So today we'll talk about organic halides, and then each day we'll just add something new. So I think after our lab tomorrow, so then Wednesday we'll do our alcohols. It'll be Wednesday. Thursday we'll do carboxylic acids. Monday we'll do esters. Those are the ones that smell. And then we must be doing polymers next week, Wednesday, I'm guessing. Does that make sense, kind of the roadmap as to what we're doing? One more thought before I go to the next slide here. The very first day I told you that I have 3 main goals for you. I know like curriculum maybe has other sub-objectives, but I had 3 main goals. One, that you'll appreciate just how vast organic chem is and how useful it is to our everyday life stuff that we have. 2, that you'll be able to name compounds. We're still going to be doing that. But now we can start talking about the third main objective, which is how do we make stuff? What sort of reactions do we utilize? You guys should ideally know a few reaction types, like say single replacement, double replacement, some of those things. Well, today we're just going to add to the list. So today we're going to do addition and substitution, I think is today. Okay, so let's talk about the organic halides. So, it's very straightforward. An organic halide basically involves something organic, so that's not carbon, and it has to have a halide, which is just the word for a halogen. So you guys know what the halogens are? It says group 17. Do you guys know them off the top of your head what the main 4 are? Yeah, fluorine, chlorine, bromine, and iodide are the main ones. I've never worked with astatine before, so don't worry about that one. But these are the main 4 you need to know. We should talk first about how they work. The functional group is the halogen atom, and it works very similar to a hydrogen. Do you guys remember doing electron dot diagrams for hydrogen? It looks like this. How many bonds can hydrogen form? 1. Well, these are very similar. Here's chlorine. It has an electron dot diagram configuration, something similar to this, where this is a lone pair. This is a lone pair. This is a lone pair. Can lone pairs form a bond? No, they can't. And it has 1, do you guys remember what this is called? Bonding electron, yeah. Bonding electron. And so we start with these ones because your halogens functionally are very similar to what we've been doing before. Chlorine basically can form 1 bond, and only 1 bond. Very similar to how hydrogen can form 1 bond and only 1 bond. So most of the molecules that we deal with today are basically going to look like something like this. I'll just draw one out here. You know how normally I draw a molecule like this, and all of those lines are kind of my shorthand notation to indicate there's a hydrogen there? Well, rather than drawing a hydrogen there, we'll just put, say, a chlorine in its spot. That's it. So this is a molecule that we'll talk about today where it still has, say, 3 carbons in a row, only rather than this being a hydrogen's been flopped out for a chlorine. That's it. Does that make sense? And it bonds very similarly because they each have 1 bonding electron. Before I get too far, though, I want to talk about the word functional group. One of your assignment questions talks about functional groups, so you can probably start doing some more of the assignment questions. I would say do a little every day now from this point on, because every day as we talk about something new, you should be able to answer a new question. So a functional group is basically a characteristic arrangement of atoms. That's like the most broad topic I could give you. Put it into people words, a functional group is kind of like a polyatomic. Do you guys know how there's those polyatomics in that little gap in your periodic table where everything kind of like sits together as a group? Okay. A functional groups are kind of similar, where it's a unique identifying characteristic of a molecule. And maybe as one of the ways I can illustrate functional groups is to go back to the very first slide of the unit. Okay, we're on 76. You guys remember this slide from when I started the unit? I even still have it circled. See this NO2 right here? That's called a functional group. It's a very unique, characteristical, like common grouping. This NO2 and this NO2. I pointed out to you guys this was called trinitrotoluene. This is the nitro functional group, which is why there's 3 of them. Does that make sense? Here is another functional group. Here is another one. Here's another one. Here's another one. Does that make sense? You know, you'll pick them out very easily because they don't contain carbon typically. They usually have something else in its place. We probably would not call that a functional group, however. We would probably call like a CH3 a methyl. Does that make sense? If it was like 2 carbons, we'd call it an ethyl. So I don't know that we'd call something like that a functional group necessarily. Does that make sense though? Okay. What did I say? Number 76 was? Here's a slide then on this side here that has a list of all of the major functional groups. We don't actually cover all of them in this course. So the ones that you do have to know are the alcohols. We don't cover ethers. I'm going to put a star next to aldehydes. I teach you guys how to name aldehydes because I think it's useful, but it's actually not on the diploma. But I think it's really easy to learn how to name them, so I kind of throw it in there as an extra slide. Okay. And ketones are the exact same thing. You don't actually have to know ketones, but I'm gonna teach you them anyways. So I'll just say these ones are not on diploma. The reason why I teach aldehydes and ketones is that carboxylic acids are on the diploma. Can you guys see how the carboxylic acid is a little bit similar to an aldehyde and a ketone? What's similar about it? That double bonded oxygen. Yeah, see how there's a double bonded oxygen right here? And here there's a double bonded oxygen. Really the difference between these is actually the letter R. And let me talk about R maybe in a second. But these two are very similar to this one right here. And so I've just found, what the heck, it takes me 5 minutes to show you how to name these two, so that in the future, if you ever do this, you've already heard them before. Okay, but I won't test you on it, by the way. I'll just show you. We do esters. Esters are the ones that smell. And we don't do amides or amides. So, although we could. I mean, basically, once you learn a rule, you just add a new ending to a molecule. So these are the ones you need to know. Alcohols, carboxylic esters, carboxylic acids, esters. And today we're going to do organic halides, which isn't even on this list anyways. So, okay, enough talking about how to make this work. Let's get started here. This is R with an X. Like, this is the most ridiculous thing to start with. R essentially refers to, if you're ever wondering what R stands for, R equals like a whole bunch of carbons. And we have no idea how many. There could be 1, there could be 2, there could be 3. One of the words that we learned about previously was called homologous, if I'm saying it right, where you could have 1 carbon in a row. You could have 2 carbons in a row. If you wanted to, you could just add more and more and more. Does that make sense? So whenever you see this notation R next to something, R just means an undefined carbon length. We have no idea how long it's going to be. Okay. For us, X today is going to be a halogen. So let me come back to the really wordy slides. Let's actually do something here. Okay, find this example. We'll just hop into an example. I'll just go back to the written slides in a bit. I would like to think that this is fairly intuitive, if you guys know what that word means. Like you can kind of figure it out on your own. If I asked you to draw a 2,2,5 tribromo 5-methylhexane, you guys want to take a stab at it without me even actually showing you anything? Because I feel like you might be able to do it without my help, actually. Give it a try. See what you can come up with. And then I'll do it with you in a second. 2,2,5 tribromo 5-methylhexane. When you're drawing a molecule, should you start with the beginning of the molecule? No, the advice I'd usually give is hop to the back, right? Start with the hexane. There's a hexane. Normally, on a hexane, you'd have hydrogens attached to every single carbon. You'd saturate this thing full of hydrogens. That being said, if I read backwards, though, on the 5, there's supposed to be a methyl. That's kind of odd. Normally, you'd think that should have a lower number than 5. But, okay, let's go with it. So, 1, 2, 3, 4, 5, 6. Right here, I'll make a methyl. I guess I can get rid of the numbering scheme now. Okay, well, again, it's an ane, it's saturated, so normally everybody should be just completely filled up with hydrogens. Except at the front it says there's a 2,2,5 tribromo. So hopefully that means to you all on the number 2, rather than this guy going to a hydrogen, it's going to a bromine. And this one's also going to a bromine. And rather than this one here on number 5 going to a hydrogen, it also goes to a bromine. Everything else, by the way, is a hydrogen then. Right, like all the rest of these lines, you don't need to draw a hydrogen there if you can figure that out yourself. But there's your molecule. Does that make sense? Anybody able to get that yourself? Okay. It's fairly intuitive. Like hopefully it kind of makes sense, right? So, why don't I go back to the wordy slides I skipped then? Because really, the more important part is probably not the naming. It's knowing some of the properties that goes along with it. Why is this useful? What can this molecule accomplish? So if you go back here, let's see, what can I point out that's relevant here? Halogens are part of the organic halides. Okay, here's some compounds that maybe you've heard of before. You guys ever heard of the chlorofluorocarbons? They were abbreviated for a long time as CFCs. Anybody know why they were really bad? Does it say on here? Does it say? More specifically, do you know what they were bad for? They were bonding with ozone. Yeah, we discovered after using these for a while, they were bonding with the ozone layer, which is bad because ozone filters out UV rays, and unfiltered UV rays are going to cause radiation, which might cause more cancer. So it kind of became a bit of a problem. There was an agreement back in 87 called the Montreal Protocol, maybe 92, somewhere way back when I was a little kid. You guys weren't even born yet. And in the Montreal Protocol, basically they decided to phase out the use of chlorofluorocarbons. Yeah, I said that right. Okay. That being said, you can't just argue, oh, all molecules with chlorine and bromine are bad. Because, I mean, here's one. Teflon. I have no idea why that A is on the end there, but Teflon involves fluorines. It is a polytetrafluoroethylene. We'll talk about how to name polys a little bit later, but hopefully you kind of get the concept here. A tetrafluoro means that it's going to have 4 fluorines attached to it. Does that make sense? And I don't think anyone's going to argue that Teflon is killing the ozone layer, right? It just makes it so that you can cook your eggs without extra butter on the pan, right? So, okay, that being said, there are organic halides that are toxic and carcinogenic. Do you guys know what DDT is? Yeah, it was supposed to be used to be pest control, and they discovered that it was accidentally killing other wildlife. I wasn't sure about eagles, but birds of some type, I believe it was. So, yeah. Anyways, those are some of the things they're used for. Here's the information slide about their properties. I haven't really focused much on properties until now, so maybe I should do a quick rehash about polarity. do you guys know how to figure out whether something is polar versus non-polar? Remember how to kind of figure that out? Yeah, the electronegativities. Okay, let me just draw a non-polar molecule. Here is, oh my goodness, Monday morning, propane. Is there a winner in the fights for all these hydrogens and carbons? Yeah, somebody wins. Probably carbon. But due to symmetry, the winner of all of these fights is kind of like neutral, if that makes sense. And so this molecule is nonpolar. What does that mean? What do nonpolar molecules, what does that accomplish? Anybody know why that's relevant? Tomorrow we're going to do a lab with organic materials, and they cannot go down the sink. It's not because they're poisonous, it's not because they're toxic, it's due to their polarity. Okay. Water is polar. And up till now, pretty much everything you guys have used has been ionic, and therefore can dissociate and it can break into pieces. Does that make sense? Polar molecules do not dissolve in water. Because water is polar, these guys are non-polar. It's like oil and water. Does that make sense? And because they won't dissolve, we shouldn't put organic stuff down the sink because much of it is non-polar. Does that make sense? Well, now let's do the same sort of molecule here. We'll do 3 carbons in a row. But rather than throwing hydrogens in every location, why don't we take one of these guys and put a fluorine over there? Now is this thing going to be symmetrical? No, now it won't be. So now it might actually be polar again, which this one might be a little bit safer than to put down the sink because maybe it will actually dissolve in water, like they'll mix together. That being said, it may be polar or non-polar. Let me show you an example of a non-polar molecule involving chlorine or fluorine. What if you put fluorine in all 4 locations? So now, yeah, it still has fluorines and bromines and iodides there, but now is it back to being balanced and symmetrical? Yeah. So now it's back to being non-polar. So it may be polar, it may not be polar. Okay. Really, polarity, really, if the question you might get on a diploma, I've seen this before, is as to whether or not it's going to like be miscible. Miscible. You guys know that word? Whether it can mix? Okay. Maybe they'll talk about solubility. If it's non-polar, it's not going to be soluble in water. If it's polar, it will be soluble in water. So you'll just have to look at the molecule and figure out whether or not it looks symmetrical or not. Okay, because of the extra fluorine, there's another thing that happens. Do you guys remember the term London forces? London forces mean that certain things have more electrons than other things, and that usually gives them a higher boiling point. If I were to compare this molecule I just drew right here, a tetrafluoromethane, to just regular old-fashioned methane, both of these molecules here are nonpolar because they're both nice symmetrically balanced. But this one right here is going to have a higher boiling point because fluorine is a bigger molecule than hydrogen. Does that make sense? You guys remember talking about this at all? Okay. If I were to compare these 2 molecules to each other, which one would have the higher boiling point? This one over here. This would be a 1-fluoropropane, by the way, when we name it. 1-fluoropropane. The reason why this one is higher is 1, because fluorine has more electrons than hydrogen, but the other reason why is that it's polar. And anything polar should have a higher boiling point because polar molecules stick together as well. That's the other thing that polar molecules can have happen. Does that make sense? And so if they can stick together, they have higher boiling points. It just means it takes more energy to separate them due to, you guys remember talking about fractional distillation? How they might separate molecules based on boiling point? It just means that this one boils at a higher rate, that's all. So these are the main things you should be able to do. You should be able to take a molecule and figure out its solubility with water, and you should be able to relatively compare boiling points. So, if you want some practice on this, I could pull out my grade 11 stuff, and we could practice just naming molecules and figuring out whether they have like low or high boiling points. Because for you guys in my grade 11 class, like we just did a whole unit on this right before Christmas, right after Christmas. So, okay, how do you name it? We've already kind of did this. You just use a prefix. So you either use fluoro, chloro, bromo, or my favorite, iodo. Kind of fun to say that. Okay, let's do some more examples. So, try to name this guy. How would you name this molecule? So I guess the first question you have to ask yourself is how many carbons can you find in a row?
7.
Looks like 7. Yeah, and I don't see any rationale as to one of them maybe having a double or triple bond. So 7 in a row makes it a hept. Ane. Okay, well, it looks like we have both a chlorine and a bromine. So we have a bromo and a chloro. Which one should go first? Alphabetical, yeah, you're right. Yeah, alphabetical. So as soon as we start attaching these to, like, say, other groups, just keep going alphabetically. So what's first? Bromo. And then chloro. The only other thing we need then is to numerically number. Well, that's redundant. Tell me where they're located, right? So you need the lowest numbers possible. So I imagine the best way of doing this is 1, 2, 3, 4, right? So means your bromines on the 2 and your chlorines on the 4. This is a 2-bromo 4-chloroheptane. That makes sense? Tell me about its properties. Polar or nonpolar? Why? I would say probably the best definition, it's not symmetrical. Right? If this was more of a symmetrical molecule, if there was, say, like chlorines on the other side over here to balance it out, that might make it less polar. But due to these just individual chlorines over here, the hydrogen up top, it doesn't have the same sort of win in the fight for electrons to balance. Does that make sense? So this is probably a fairly polar molecule, which means it has probably a relatively high boiling point. Right? Due to its polarity, it's going to stick together a little bit better. As we learn about more and more functional groups, we're actually going to rank where they should fit on the boiling point scale. In terms of, like, this one's the best, this one's the next best. So since we actually only have one functional group we're talking about today, we can just say it's relatively high. But like on Wednesday when I add in alcohols, I'll tell you that alcohols are actually higher, and I'll explain why. So we can make a list of ranking these things at some point. That make sense? Okay, cool, let's move on. Try drawing me a dichlorobenzene and see whether you can try to find all 3 isomers. So there are 3 isomers of a dichlorobenzene. See whether you can try to draw all 3 of them. So you need a benzene, you need 2 chlorines on it. All right, well, here's a benzene ring. Benzene normally gets 1 hydrogen in each location, right? Well, dichloro means put some chlorines instead. So I guess I could put a chlorine right here and here. This would be a 1,2 dichlorobenzene. I could put them here, 1 and 1, 2, 3. 1, 3 dichlorobenzene. I could put it at 1 and 4 dichlorobenzene. Why not 1 and 5 though? Yeah, 1 and 5, if I try to put it back over in this spot right here, it's the same thing as this guy right here, just flipped around. So that doesn't actually count as something new. So this would be the 1,2 dichloro, this would be the 1,3, and this would be the 1,4. Tell me something about their properties. Polar or nonpolar? What about the 1,2? That looks fairly polar, doesn't it? There's quite a bit of pull on this direction over here that these hydrogens over here just won't be able to exert quite as well. Does that make sense? Even this one right here probably is going to be fairly polar. What about the last one? Okay, truth is it actually is going to be slightly polar still. The reason why, don't forget these things are in 3 dimensions. And so technically there is a little bit of an up and down factor as well, like in and out of the board. Does that make sense? So Although this will be the least polar of all of them, it probably is not completely non-polar. We don't get nearly into that much detail in this course, but chances are this molecule would actually still be slightly polar, but nowhere near as polar as this one here, just due to its geometry. Does that make sense? Like if I were to draw it in 3 dimensions, I don't even know that I could, but imagine you have kind of a flat molecule. You might have like one chlorine that bends a little bit up, perhaps, but then the other chlorine bends a little bit down, perhaps, instead. So we don't actually have the ability to have this. Well, maybe I could do this. You guys remember this sort of notation where you have like a dark line to indicate coming out of the board, and then like a dashed line indicating that it goes into the board? Since chances are it's not all flush with the wall, as soon as you have a little bit of tilt like that, then that probably adds a little bit of polarity to it. So, okay. Do you guys feel like you have enough to take on this challenge, though? Well, try it. There's 7 of them here. Name them. Why don't I give you 5 minutes? See how far you get. Why don't we name these 7 here, then we'll take a break. And then after the break, we'll talk about how to make these molecules. Because that's the last part of the equation, not just naming them. Naming them hopefully is going to be the easy part of your job. The harder part is how do you make them? What sort of reaction types do it? So, but why don't we take a break before we do that? If the line is being drawn, by the way, to the bromine, chlorine, or iodide, that is taking the place of a hydrogen. Does that make sense? So, like when you're looking at this first one right here, there is not a carbon right here as well. This carbon is going to a bromine, and therefore must be going like to a hydrogen somewhere else. So don't think there's an extra carbon sitting right there, by the way.
Those benzenes are just cyclohexanes.
They're cyclohexanes. In order to be a benzene, they'd either have to show a double bond alternating scheme, which is not true anyways, because we know the bond lengths are all the same, or they'd have to draw a circle in the middle. So yeah, good question. So the middle ones there that have the hexagon, don't call them benzenes. They are cyclohexanes. Seems really good. Just so you guys are aware, ignore you. Okay, just so you guys are aware, on the diploma exam, by the way, they've very specifically stated that you will get either a double bond or a functional group, but they're never going to combine them together. Does that make sense? Technically, in real life, like I said, if you can dream it, it exists, and there is a naming scheme for that. Well, they're also going to make it so that you get only one type of functional group. So either you get a bromo, or you get an alcohol, or you get a double bond, but they're actually not going to put like a whole bunch of stuff all together, which is kind of nice because it simplifies the naming scheme. Because you can imagine that at a certain point, like, what if you have an alcohol and a bromine and a double bond and a whole bunch of ethyl groups? Like, it becomes way too complicated. So for our purposes, we do simplify it so that you just get one of something. That's it. Now, you could have a cyclo still inside that. So you could have a cyclo with the double bond. You could have a cyclo with the bromine. But you basically get one or the other. Does that make sense? So, anybody want another minute? Okay, let's do these verbally then. This one up here in the top, what is that, left-hand corner? It looks like there's 7 in a row. We need a bromine and we need a methyl group. So bromo is going to go before methyl. We need the lowest numbering scheme possible. So I believe the lowest numbering scheme would be to call the bromine a 5-bromo, a 2-methyl heptane. Let's do that again. A 5-bromo, 2-methyl heptane. Does that make sense?
Would you ever go like the other?
It would have higher numbers because then it would be 1, 2, 3 bromo, 6 methyl. And you want the lowest numbers possible? Does that make sense? Maybe I should write it out then. If I number it 1, 2, 3, 4, 5, 6, 7, I'm using a 2 and a 5. But if I go the other way, 1, 2, 3, 4, 5, 6, 7, then, does that make sense? 2, 5 is definitely lower than 3, 6.
I thought it was like for the first one, you want the lowest number.
Okay, maybe I should clarify that. The precedence always goes to a double bond. Since we're not going to be doing any double bonds, that's really not relevant to us because we're not doing one of each. Does that make sense? So we just want the lowest numbers possible. So bromine doesn't take some sort of magical priority. Does that make sense? So give it the lowest numbers you can. Should I write it out or just is saying it verbally enough? Okay, so it's going to be a 5-bromo, because that's alphabetically, 2-methyl heptane. Why don't we go down the next column here? Right here, you've got a cyclohexane, and it's going to have a dimethyl, but methyl is going to come after fluoro. So we're going to need to have a fluoro and a dimethyl, and we need the lowest numbers possible. The lowest way of doing this is to go with, like if I go 1, 2, 3, 4, that's the dumbest way of writing the number 2. That's a 1, 3, 4. But if I change the way I write it up a little bit here, it is possible to have a 1, 2, 4. So alphabetically, it's going to be a 4 fluoro, 1, 2 dimethyl cyclohexane. Let's do that again. 4 fluoro, because fluorine is alphabetically first. 1, 2 dimethyl, because then methyl is next. Don't forget the di in the word, by the way. And then it's a cyclohexane.
I keep doing it.
You have them in the wrong spot? There's a very likely chance that they'll make a multiple choice question, and like they'll make those the distractors, right? Where you change around just the littlest details. Okay, this one here, we need to make sure we have a carbon branch that includes all of your chlorines. You can't have a chlorine on a methyl branch. So you have to make that be your set. Does that make sense? You can't have it look like this. The reason why you can't do that is because there's a methyl right here. But you can't have a methyl with a chlorine on it and still find a way to name it. So you have to try to find a way that includes all of the carbons. The functional group of the chlorine is all attached to it. So it looks like we need a chlorine, a chlorine, a chlorine. So we're going to have a trichloro. So at some point in the word, you should have trichloro. Hey,
Breakfast.
anybody hungry? Thanks. Okay, so we need it.
Die of lack of nutrition.
Probably not. Okay, we need a trichloro. We also need a methyl and ethyl. And we need the lowest numbering scheme possible. I imagine that's going to be starting here. This would be a 1. And then we'd have a couple of 2s, a 4, and a 6. Because if we start on the other side, we're going to have like a 7. So hopefully you have, let's see, alphabetically, ethyl. You need a 4 ethyl. No, chlorine's before ethane. Take it back. You need a 1, 2, 6 trichloro. Then you need a 4 ethyl. Then you need a 2 methyl. 5, 6, 7 heptane. Does that make sense though?
Yeah, I did the.
Okay. You just need some practice. Okay, this one right here is not drawn out, but basically you have a carbon with 3 hydrogens, and then there's a bromine on it. This is bromomethane. We don't need a number. Why don't we call it a 1 bromomethane?
Oh, I guess you can just.
All of them are on the number 1. Does that make sense? Or, like you said, if you just rotate the molecule, I mean, they're all on the number 1. So this guy's just called a bromomethane, because you don't need to have a number on it. That's redundant. This one here, though, we do need a number. I think I chose these ones side by side on purpose. This one is a 2-chloropropane. We do need to put a number on it because if you attach the chlorine over on this one right here instead, then it would be a 1-chloropropane. So 2-chloropropane. That being said, this one down here is just iodocyclohexane. We don't need a number because whichever one you attach the iodide to is the number 1. And if you put it in the next spot over here, then it just rotates the molecule. So this is iodocyclohexane. It's fun to say. Iodo.
Yes.
Okay. Okay, the last one here, we need to have 5 carbons in a row, it looks like. Lowest numbering scheme probably means you need a 2 bromo. And then you need a 2 and a 4 with a dimethyl. And then it's a pentane. 2 for bromine, 2 and 4 with a dimethyl. Sorry, that's a horrible writing there. Dimethyl, and then pentane. Sound good? Okay, the more practice you get, the better you are at this. I need you guys to take a break because we still have half a lesson to do. That's just the naming part. When you come back, we got to talk about how to get these molecules where they are. So, take 5. Okay. If you guys have your assignments, can you pull your assignment out real quick here? I want to talk about a few more questions you should be able to answer now. The assignment's only got 7 questions. I think it was 7. Can I ask that you guys make sure you try to do it in advance this time? A couple of you are a little late on the last one around. It doesn't serve your needs to do it after the fact. So, not that you need a lecture from me, but let me just point out a few more questions you should be able to answer now. Like say number 2. I just give you a preamble saying there's a million isotopes involving carbon. You should now be able to do number 2 if you want to. Draw and name an 8-carbon organic compound that contains a functional group. Now granted, we've only learned 1 functional group, but if you want to, you could just throw a bromine onto 8 carbons and then name that thing. So it could be like a 1-bromo-octane, or a 2-bromo-octane, or a 3-bromo-octane, or a 4-bromo-octane. But not a 5-bromo-octane, because if you can picture it in your head, as soon as you go to the 5th one, it's actually the 4th one from the other side. Does that make sense? So there, you can answer number 2. Because then number B says draw and name 3 structural isomers for the compound you just drew. So that'll take you all of what? 2 minutes to do? So anyways, the advice I'd give though, as we learn new functional groups, do the questions involving those functional groups. Number 3, you can see here, involves some chlorines on it. And so we're going to talk about the reaction on number 3 there right now. The reaction that takes that C6H6. What's C6H6?
Benzene.
Good, it'll be benzene, right? 6 carbons, 6 hydrogens. Add chlorine and make C6H5Cl. So what it looks like's happened on this reaction here is one of the hydrogens has come off, a chlorine has taken its spot, and the other byproduct is hydrochloric acid. So After today, you should also be able to do number 3. That being said, number 4 we probably can't do yet because you can see that the name for number 4 involves OL at the end. And we just haven't learned that ending. That's an alcohol, by the way. We'll do that on Wednesday. So, anyways, let's do the second half of our lesson here then. So now I need to teach you guys how to get these molecules made. Because you don't find these ones typically naturally. These are synthetic compounds that scientists have developed, found a way to, if I add this to this, hey, look, it makes this. That's really cool, right? And we discover that this one's Kevlar, this one's acetaminophen, this one is crystal meth, right? I mean, some of them are better than others, some of them are more legal than others, but like they each have a use. Does that make sense? You don't find crystal meth growing on a tree. Does that make sense? That's probably a good thing, right? But like we don't find aspirin growing on a tree. Technically, actually, aspirin has been found in willow bark, but you get what I'm saying here? Like, we have to make these compounds. So that's the last part here is how do we synthesize and create them? So today we're going to talk about addition. Addition is probably like you'd think the word would say, right? You need to basically take a molecule and add it. Here's the key thing about addition. Addition does not create 2 byproducts. You take molecule A, you take molecule B, you combine them together, and it just makes one thing. It's kind of like formation. Take this guy, add them together, and just produce a single product. I should point out, almost everything we talk about at this point here usually requires a catalyst. When you get to university, this is where organic chem sucks, actually. You have to start to learn how the catalysts work, and usually it's like a multi-step process where the catalyst will cause this molecule to rip apart, then it'll reform itself, then something else will happen, then the actual molecule you care about will attach itself, then it'll replace itself, and then it'll pull off something so that the catalyst actually isn't consumed itself. And so you have to memorize like these 5 or 6 step processes. For you guys, all you have to do really is just know start, finish. Does that make sense? But I just need you to know that catalysts are usually involved. So here's a very good example of an addition reaction you guys have already learned. Take a but-1-ene with a double bond, add some hydrogen. It's actually a special name we assign to this. Anybody remember what we call it? Hydrogenation. Good, yeah. Hydrogenation. Add a hydrogen molecule to something. Take a molecule and make it saturated. Well, we're going to do something very similar, only rather than with hydrogens, we're going to do it with chlorines. So here is an ethene. You've got double bond. You can see there's like a gap sitting right here, right? Well, if we add chlorine gas, isn't it very intuitive that the chlorines will just take this spot right here? There, you got a 1,2-dichloroethane. That's how addition works. So for addition to occur, if I want to put like a big star next to this, it needs to be unsaturated. Unsaturated. If you have an unsaturated molecule, you should be able to add something into that empty gap. Break the double bond, throw something in its spot. Here's some more pictures. Who was I talking to earlier about how many slides there were? I think that was Driana. There were so many slides on this one. We're at the picture stage though, right? Where most of this is just looking at how these mechanisms work. Here's an ethyne. Hopefully you can see there's a gap here and here and here and here. So if you add a single bromine first, hopefully you'd kind of see, well, the bromines, they'd fill in like, say, 2 of the gaps. Sometimes we use the phrase adding across a double bond. It would not be valid for you to put that bromine right here. Why would that not work? Not symmetrical. Count where the bonds would be then. It means that you wouldn't be able to have a double bond right here because you'd have 1, 2, 3, 4 bonds right there. And then this carbon right here would only be bonded to this carbon and not hydrogen, and it wouldn't have enough there. So when you add something across a double bond, you have to put 1 on each side. Now, I don't care whether you draw it like this one here did, where you draw one of the bromines going up and one going down, or whether you were to say put this bromine down here. Like either one would be fine, but you definitely cannot put that bromine right here. Does that make sense? Like bonding rules would dictate that this carbon over here wouldn't have enough stuff attached to it. This particular diagram then shows that after this triple bonded molecule becomes a double bonded molecule, it could then subsequently react with another bromine and then become single bonded everywhere. But now, rather than having some hydrogens, literally everything is a bromine, well, except for the two N cap ones, obviously. Does that make sense? Tell me something about the properties of this molecule right here. Still probably polar. Keep in mind, even though you might argue that, hey, look, these arrows cancel each other, it's in 3 dimensions. And so it seems fairly unlikely that in 3 dimensions, as soon as I start doing like a, I guess I remember drawing like this, carbon to bromine to like a hydrogen to a bromine to a carbon to like a hydrogen, bromine. You guys remember drawing with like some of those symbols like that? I don't think this is going to be symmetrical because this one's kind of pulling out of the page. This one's going into the page. This is coming out of the page. So that being said, if all of them were bromines though, if you could find a way to make this molecule with all bromines, then it would be nonpolar. Does that make sense? So, but you should be able to tell me that this molecule right here is polar. It probably has a fairly high boiling point. It's probably a liquid, not a gas. Does that make sense? Okay. What else do we got here? Here is an addition reaction, but we're not going to use something diatomic. Okay. The last examples I showed you involved adding chlorine with chlorine. What if you add hydrochloric acid? You add 1 hydrogen, 1 carbon. Well, you've got this gap right here, right? What you could do is you could put the hydrogen in the first spot and the chlorine in the second spot, which means that you'd get this molecule right here, a 2-chloropropane. But what happens when this molecule attaches right here? What if it didn't attach hydrogen here, chlorine here? What if it attached chlorine here, hydrogen there? What if the molecule came in the other way? Do you guys see how it would make a different molecule? Because now the chlorine would be attached in the one location. And so what often happens is it's going to create structural isomers, where about 50% of the time you'd create this molecule, and 50% of the time you'd create that molecule. So you'd actually get like a probability attached to it, where we're actually not sure which one it would create. How would you separate these two compounds? If you took propene, added hydrochloric acid to it, and you ended up getting 2 different products in equal proportions, how would you separate them? Boiling point, fractional distillation. They do have unique properties. One of these might be just slightly more polar than the other one, and so the boiling point for one might be 78 degrees. The boiling point for the other might be 71 degrees. Does that make sense? Okay, bit of a story time actually, bit of an aside here. Have you guys ever heard of thalidomide? No one's ever heard of thalidomide. Okay, thalidomide is a chemical, a drug that was developed back in the, I want to think 1960s. And it was given to a pregnant woman who had morning sickness. So like when someone's pregnant and they want to not throw up all the time, you know, this was a drug they gave them. Anyone ever heard of thalidomide babies then? They were a generation of, I don't really know what the right word to use. They were born with defects, where some of them didn't have arms or legs or hands, things along those lines. You've heard of this now? It should be a biology concept, yeah. But there's an interesting chemistry concept to it. Thalidomide, we didn't discover this until way later. Thalidomide actually made 2 different isomers of each other. One of the isomers of thalidomide, perfectly safe. Definitely cured the morning sickness, women wouldn't throw up anymore. But the other isomer that was produced during the process, that was the isomer that caused the defect. So depending on which of the 2 isomers you ingested, depended on whether or not someone actually ended up giving birth to the defect, I guess. I don't know what the right word to use, politically correct word is, but the ones with the deformations. Does that make sense? It was actually based on isomerism. And they didn't realize that there were 2 isomers, both of the same chemical being given at the same time. So anyway, side note story. Okay, let's keep going here. Let's do this example here. Chloroethene is made from a two-step process involving ethane. An alternative method, though, is to react ethine with hydrogen chloride. Let's try to write this equation. Let's see how this would look. So first we want to start with ethine. What does ethine look like? Triple bond, which means you'd need what? Just one hydrogen kind of capping the ends. So you'd have like a gap right here, and you'd have a gap right here. Does that make sense? And we are going to add a limited amount of hydrochloric acid. So we're going to add HCl. Well, hopefully you can kind of visualize what's going to happen. We're going to limit the HCl so that only one reaction takes place. The HCl can, like, say, take over the spot, which means you'd still have H to C to C to H, but now your H and your Cl will show up there. You kind of picture how the H and the Cl are going to kind of take over that location? Saturate the molecule. However, we're going to do it with limited. So if we use lots of HCl, it's possible that an HCl could also saturate the bottom of the chemical, but we're very, very going to limit the amount of HCl we use so that there actually still is that gap down here. And now we've made ourselves a chloroethene. Chloro because there's a chlorine on it. Ethene because there's a double bond. By the way, you guys won't do that. You'll either do a chlorine or you'll do a double bond on the diploma. You should do one or the other. But I mean, this one's not too hard to figure out, right?
Do you have to care about the catalyst?
No, I mean, you just need to know that catalysts exist. So, like, it is a much more complicated method than just, look, here, literally they go together. Like, it takes more effort than that. I just need you to know that catalysts, you need to know that catalysts increase reaction rate, so it happens faster, and catalysts lower activation energy, so that they happen more effectively. So, if you had to write out the equation, then this would have been C2H2 plus HCl made CH2 CHCl, something like that. There's your reaction. One of the cool things about organic chemistry, usually balancing looks like this. 1:1. Usually you don't have to really worry too much about balancing. Usually it's always a nice 1-to-1 ratio. I can't say that that's a guarantee, but it's usually the case. That make sense? Cool. Okay. The second reaction I want to talk about is called substitution. And substitution, like its name implies, means that something's getting replaced. Addition always involves an unsaturated molecule. Substitution is going to involve a saturated molecule. The reason why these things need to be saturated is that there's not a double bond to add something across. We have to replace something. In my mind, I think single replacement. So like you can see this first compound here is propane. Propane has no double bond, so there's no logical spot for this bromine right here to get added across. So the way that these reactions work is you have to take one of the hydrogens and pull it off. Like say this one right here. We have to rip this hydrogen off. That makes sense? And then of this bromine molecule, one of these bromines gets to trade places. Not both. That's the most common mistake kids make. When they do substitution, they take two things off and two things off. Like they take off two hydrogens and they put on two bromines. It's a 1-for-1 swap. Does that make sense? So here, this bromine right here flips out with that hydrogen, and that's where this molecule comes from. That's called substitution. Here's the question though: which hydrogen does it break off? Well, the answer is any of them. They all could get broken off. So right here, I've written actually two different isomers that could exist. You could take off this one right here. That would make it a 1-bromopropane. But what if the bromine changed out this one right here? Well, then it would be the 2-bromopropane. What if the bromine changed out this hydrogen right here? What would that make it? It would be a 1-bromo. I know it doesn't look like this molecule here, but like flip it around in your mind if you can. If the bromine replaced this one, this one, this one, this one, this one, or this one, it would make the 1-bromo. Because all of those would be kind of capping the ends. But if it replaced this one or this one, it would make a 2-bromo. So both reactions will happen simultaneously. When we do this tomorrow, we're not doing this particular reaction, but it is actually possible that you're going to make 2 different products. You could make a 1-bromo and you could make a 2-bromo. And my question for you is, what percentage would it be? Now, you're never going to get this on the diploma, by the way. I just throw this in because of, I don't know, I teach math as well. I would say that 75% of the time and 25% of the time would be the ratios. Do you guys think you could figure out how I figured out those numbers?
Because there's only 2 hydrogens that the bromine can switch with on that side.
Yep.
And there's 6 on the other.
Out of 8. Yeah. Does that make sense? You won't get asked this, by the way. I won't test you on that. But hopefully that's reasonable logic. If you were to do this reaction, you would get some 1-bromopropane. You'd get mostly 1-bromopropane. You'd also get some 2-bromopropane. But this one would be more likely. How would you separate them? I'd go boiling points. They are different molecules. Although they are very similar, they should have different boiling points. So just set the temperature between the 2 boiling points and then distill it. Okay, I want to make sure I'm really clear on this one more time though. Substitution involves taking one of the bromines and switching it with one of the hydrogens, not both of them. So one of the unique properties of this is that you always are left with a byproduct. Unlike addition, where 2 things just come together and just stick together, you're done. This one always has a byproduct, and that byproduct is typically going to be an acid. The reason why it's going to be an acid is because you pulled off one of your hydrogens, and that hydrogen now gets to go with the remaining halogen. So you're either going to get a hydrobromic acid, a hydrochloric acid, and a hydrofluoric. Does that make sense? So you're typically going to have an acid left over. Which maybe can go to another point here. When we do our esters lab, granted esters have a different reaction here, but we would never actually drink or taste this. Does that make sense? Because there are other byproducts possibly here. So, here's another example. We can actually still do this with benzene. Benzene is considered saturated, remember? Even though benzene, sometimes we draw them with double bonds, they don't actually have double bonds. So this benzene right here has hydrogens all scattered around the periphery of the benzene ring. Well, we can do a substitution reaction then, where we take the chlorine right here, and this chlorine can replace with any of the ones we want. So replaces with this one right here. I want to talk about this line right here though. The tricky thing about substitution is that the longer you leave a substitution reaction, the more hydrogens can get ripped off. So for example, in this one right here, it looks like this hydrogen and this chlorine have been replaced. But if I leave this for like say a couple of days, eventually a chlorine can rip off this hydrogen as well, and this hydrogen as well. And eventually you could have a molecule where there's no hydrogens left. It's completely saturated with chlorines. Do I have a picture of that here? No, let me draw a picture here. Imagine that I just used a good old methane molecule. Let's say I reacted it with chlorine gas. What could happen is this hydrogen and this chlorine, they could switch places, and you'd have CCl with H's everywhere. Does that make sense? But let's say I leave it longer, and it's still soaked in chlorine gas. Well, now those ones can trade places. So now what we have is this hydrogen, this carbon, this hydrogen, and now there's 2 chlorines on the molecule. Does that make sense? Well, let's say I leave it even longer. I'm not going to do this all the way through, but keep reacting. Eventually I could have those ones take places. Does that make sense? So one of the key indicators for this thing right here is time. The longer you leave this thing saturated in its diatomic molecule, the more different molecules you'll make. The point I need to make here, though, is that these are not isomers of each other. This molecule right here and this molecule right here, they're not isomers. They actually have different stuff. Does that make sense? This one has 1 chlorine. This one has 2 chlorines. So even though you can have multiple reactions taking place at the same time, unlike this reaction back here, where both of these happen at the same time and makes 2 different molecules, these are isomers of each other because they have the same stuff. If you do this reaction right here, wherever I was drawing it, and you leave it for a long time, they won't create isomers of each other. It'll just do more and more reacting. So sometimes you have to stop your reaction after a set amount of time so that it can't make an accidental further byproduct. Does that make sense? Okay, let's start getting to the end here. That's another example. Is this my last one? Yeah, okay. Okay, so this one actually talks about CFCs, the air conditioner refrigerants that are now banned. As I read through, what do I actually have to do here? Here we go. The carbon tetrachloride was produced by reacting methane with chlorine.
Getting tetrachloride to C12.
Yeah, I think we just want to talk just about this, though. Eventually we'll get to C12H, that one there. So let's just do this little bit here, though. So first what we need to do is we need to take carbon tetrachloride and make it from methane. This is what I just did, actually, with chlorine. So what's going to happen at first? Well, at first, you're going to have 1 chlorine. But you know what I skipped last time around? I didn't write the other byproduct. What's the other thing that it's going to produce? Yeah, HCl. Because what happens is this chlorine and that H switch places, but you get some HCl. So that's step 1. But then this guy right here would react further. And I think I'll just draw one more equation and then we'll figure out the net when we're done. We'll add some more chlorine to it. And it would then make something like this. Now there's 2 chlorines in the molecule with another HCl. Does that make sense? How many reactions would it actually take? I think it would take 4 reactions to do this, right? At the end of the day, the net of those 4 reactions is you would need to take your methane, and since you need to react it 4 times, you're going to need 4 chlorine gases. That makes sense? It would then make you a CCl4, which has got, rather than 4 hydrogens around it, it would have 4 chlorines around it. And each of those reactions would produce an HCl. So you'd have 4 of those. Does that make sense? So this would be the one time where I'd say it's not a 1-to-1-to-1 ratio because of the fact that we did 4 reactions. We took this guy, made it CH3Cl, then CH2Cl2, then CHCl3, and then finally we got it to CCl4. And the biggest indicator is that we just need a lot of time for this to happen. The longer we let it sit, the more that it occurs. Does that make sense? Cool. Okay, let me stop, if that made sense to you. I have a couple other slides here to point out. Technically, when you get to a higher level of university chemistry, there's actually different ways that you can draw these. See how both of these chlorines have been drawn on the same side of the molecule? And then here they've been drawn on opposite sides of the molecule. Those are actually known as isomers of each other as well. But we don't cover that in this course. But in case you're wondering, like, does it matter where to put the chlorines? The official answer is yes, it does matter where you put them. However, for our purposes, if you draw both chlorines on the bottom, or one on the top and one on the bottom, we don't actually care in this course. But this is the thalidomide thing. Cis-thalidomide, perfectly good for you. Trans-thalidomide causes babies born without arms. Right? And it's just the slightest little tweak as to do you put both chlorines on the bottom or one on top, one on bottom. So. Okay, there's a summary. So let me just do my summary then. I need you guys to, 1, appreciate that this stuff is useful in the world. Hopefully you'd agree that, yeah, we make stuff with chemicals. 2, can you name it? 3, this is the new thing. Do you know the 2 reaction types? So the 2 new reactions are addition. You have to have a double bond in an unsaturated molecule. Benzene does not count. Okay? You add both sides of a diatomic thing across a double bond, one on each side. Does it matter whether it goes like top and bottom or on both sides? Technically, yes. But for our purposes, no, we're not going to do that. Okay? That's addition. Substitution, it has to be a saturated molecule. You have to add a diatomic molecule again, rip one off, put the other one in its place. It's always a 1-for-1 swap. Okay? One more thought. You often get multiple reactions occurring at once. You do need to know that multiple reactions can occur. You don't actually have to do probability like percentages. I don't think it's hard to do percentages, but you do need to know that you can actually make isomers while doing these reactions. That's my lesson. Any questions? All right. You have about 15 minutes. Maybe print off tomorrow's lab. Tomorrow we're doing a lab. Maybe do questions number 2 and 3 on the assignment. Other than that, we're done for the day. Oh, I guess one more thought. If you can, get me a progress log. Can you get me a progress log? If we still have stuff to do, we'll talk. Tomorrow. Is tomorrow okay?
No, I have kindergarten.
We do it Wednesday? Okay. Sorry, I thought we said Tuesday. That's fine. You can have a couple more days to work on it then.